We will continue our discussion on the relativistic quantum mechanics. So, we talked about the Klein-Gordon equation that a relativistic wave function, a relativistic particle satisfy, and we also mentioned the difficulties with the Klein-Gordon equation. We will come back to the difficulties later, but let us continue our discussion now considering the particle interactions. At first, we will consider the electromagnetic interaction. So, electromagnetic field can be described by potentials. Okay. We will denote this by A mu, and the zeroth component is the electrostatic potential phi, and 1, 2, 3 components are essentially the electromagnetic. So, the magnetic vector potential. So, now when we consider classical electrodynamics itself, we can consider this potential for vector potential, okay, in terms of phi and 3 vector A in non-relativistic case, and in the relativistic classical electrodynamics we can consider them as components of 4 vector A mu. And if you look at standard textbooks of electrodynamics, which also includes the relativistic classical electrodynamics, then you will see that if you have a charged particle with momentum p, okay, and if you want to introduce electromagnetic interaction of this particle with the some electromagnetic field represented by A mu, then you can take the free case and consider or go to the interacting case by taking the 4 momentum p mu to p mu plus E, the charge of the particle times the potential A mu. So, here we are specifically considering a particle with electric charge E. Otherwise, you will have to multiply it with the corresponding charge of the particle along with that. So, since we have p mu represented by the 4 vector derivative dou by dou t and gradient, p mu will have actually a minus this one, minus I gradient, where we have taken unit of h cross equal to 1. So, from classical to quantum we will go to, okay, so this is the quantum mechanics. From classical to quantum mechanics, what we have to do is to consider the momentum as the operator. So, p mu is basically I dou by dou t and minus I gradient. And if we consider or this the compact notation, we can take it as I dou mu. And in the interaction picture, we have to take I dou mu to I dou mu, which corresponds to the momentum plus E times A mu. A mu is at this moment the electric field with the vector potential in the quantum picture corresponding to the electromagnetic field considered. We will see that we will be able to quantize this later on. We will see that we can interpret A mu as the particle or the quantum or representing the wave function of the quantum of the particle corresponding to the electromagnetic field, which is photon. Now, with this, let us look at the Klein-Gordon equation. Klein-Gordon equation for a free particle, we had dou mu or P minus I dou mu minus m square phi equal to 0. This gives P square plus m square phi equal to 0. Now, interacting case, when we switch on the interactions, we will have I dou mu plus E A mu, I dou mu plus E A mu instead of I dou mu, and then m square as usual and acting on phi. Expanding, this will give you minus dou mu phi plus I E A mu dou mu phi plus I dou mu phi A mu plus E square A mu minus m square mu phi minus m square phi equal to 0. This is basically clubbing all the non-interacting, the free case and then the interacting case separately. Multiplying firstly with a minus sign, I get dou mu plus m square acting on phi, which is basically the free part of the equation, plus I E A mu dou mu plus dou mu A mu phi. Sorry, here there is a mistake that we made in the earlier expression. It should have been dou mu I dou mu A mu phi. Okay. So, this plus E square A mu phi equal to 0. Now, this has two terms which should correspond now to the interaction of the electromagnetic field with the charged particle phi. Phi was missing there, so I just added that. Call this the vector, the potential. So, let me rewrite this equation as dou mu plus m square, which is the free part acting on phi, plus V phi equal to 0. So, this is the usual way of writing the kinetic energy term, mass term and the potential term. So, potential here is essentially minus, that means the minus sign also here, should have been more careful. So, minus I E A mu dou mu phi plus dou mu A mu phi plus E square A mu all right. So, this is again the potential operator. So, there is no phi as such there, A mu and the whole thing is a vector, is the potential which acts on phi. Now, let us consider the transition amplitude T f I in this case. Let us say in the interaction case, what we are interested in is, if you have an initial particle, after interaction what happens to that particle is one interesting question. So, this transition amplitude we had written earlier in the case of non-relativistic quantum mechanics, as the final particle wave function, h interacting and initial particle wave function. This I will remind you, this was done to first order in perturbation. So, if you consider the perturbation theory, the first order correction or first order to first order, the transition amplitude is given in this fashion. So, in our case, when we actually have interaction written as in terms of the potential, it is basically V phi I, and for us this is minus I interaction, right. There is a minus I missing if you look at it carefully. So, I will take the position representation and write it as phi f star V phi I d 4 x. For the potential that we just now considered, we can write this as minus I interacting integral phi f star and the potential, which is minus I e a mu dou mu plus dou mu a mu plus actually a minus, because the minus, right. So, this is a minus e square a square phi I d 4 x. So, another mistake here with the sign. So, we should have taken it as okay. This is the transition amplitude. We wrote the first order term. Now, when you consider the second order perturbation, you will have essentially the square of this thing coming in here. Of course, there will be other things changes, but essentially this will be square of the potential that will come in. When you look at the square of the potential, you will have actually the first term square will have an e square times whatever else comes with that, and then there will be an e cube, which is a cross term between these two terms in the potential, and there is an e power 4 term. Important thing is to notice the e square term appearing in the second order correction. So, we will take an approach that instead of taking the first order, second order in expansion of V, we will look at what is the order in E square, E, what is the power of E that appears in this thing, in the expression. If you do that, you will see that if you include the higher order terms, there will not be any more term which is linear in E, which will have which is proportional to E, the charge. When you consider the next order, that is E square, we will see that there is already a term proportional to E square in the first order perturbation, but then there will be other E square terms coming from the second order. So, if we want to take all the terms to the E square order, then we will have to go to second order in that case. What we will do here is, since we are not going to consider the second order perturbation theory, and to be consistent, keeping only the same, keeping the correct interactions at the same order of E, we will keep only the first order term and then discard the second order term. This can be done also because E square is very small quantity compared to E, right, and E square itself is of the order of 10 power minus 2, and E is going to be therefore order of 1, and then there is an order of magnitude difference between these two. So, we can actually neglect it easily. Okay. So, essentially keeping only order E T f I is equal to minus I integral phi star minus I E a mu dou mu phi plus dou mu a mu phi d for x. So, the second phi, first phi is the final phi, second one is the initial phi. Now, let us take this T f I and look at it closely. Phi star minus I E dou mu a mu plus a mu dou mu phi I d for x equal to minus I integral minus I E phi star dou mu a mu phi I plus phi star dou mu phi I a mu. First term I will write as minus I E phi star phi f star dou mu a mu. We will actually write it as a total derivative, right. So, we will write it as a total derivative acting on the total all of the terms phi f star a mu phi I d for x. So, let me split this. So, from this term, to get the first term in the earlier line, we had to subtract dou mu phi star a mu phi I f d for x, and then the remaining term integral phi star dou mu phi a mu d for x. Now, look at the first term. The first term is derivative term integrated over volume for volume. So, that is going to give me, so let me look at that. So, integral dou mu phi star a mu phi d for x is equal to phi star a mu phi. Okay, the subscripts, this is a mu phi I at the boundaries. What do I mean by that? Look at this, integral dx 0 to 1. What is this? Right, so it's not a, okay, integral d by dx of f dx 0 to 1. What is this? This is equal to value of f at boundaries 0 and 1, which is equal to f x equal to 1 minus f x equal to 0. So, this is a one dimensional case and the boundaries are 2 points, line integral. Boundaries are 2 points, the ends of the line segment over which you are integrating in, and that will give you value of the function at the two boundaries or the difference in lattice. Similarly, here this is the boundary of this, and it is a 4 volume that we are considering integrating. So, at the boundaries, meaning it is the boundary of that 4 volume, which means essentially the surface of the 4 dimensional space. Now, see what we are usually doing is we are interested in is a particular kind of something happening in a particular region. Let us say electron interacting with some nucleus or something. So, if you take a large enough volume, then whole thing is happening inside this. So, there will be a beam generated and then it is going in, and there will be a detector that you can put here to detect this, etc. In any case, essentially you can think about everything happening in a large volume V and integrate over that, and outside there is no field, there is no wave function, there is no particle or there is no potential. So, the electromagnetic potential exists only in a small local space or in the volume V, and outside the volume V this is equal to 0. Similarly, the wave functions, initial and final wave functions also we will consider to be present within the volume. In that picture, these values of phi f, phi I, a mu, all of this will vanish at the boundaries. Phi I star equal to phi I is equal to 0 at the boundaries. So, is phi f and a mu all are equal to 0 outside. So, on the boundary also. So, therefore, this integral therefore vanishes. Phi star a mu phi I d4 x is equal to 0. Coming back to our expression for T f I, the first term vanishes. Second term is this. So, let us write that down. So, we have a minus I T f I is equal to minus I e integral phi star f dou mu phi I. Okay. This is essentially the last term here, and the second term is a with a minus sign there, minus dou mu phi star phi I acting on multiplied by a mu d4 x. Now, what is this term here? So, we have phi f star I phi f star dou by dou t of phi I minus phi dou by dou t of phi star. Earlier we had denoted by rho probability density. Now, we have here minus I or E. So, we have actually minus I E phi f star dou by dou t phi I minus phi dou by dou t phi star. This is what we call rho. Okay. And we call this the new rho the charge density. We have multiplied the probability density though. Well, let me put this under quotes, the probability density for the way we had defined earlier, and then put this as a probability density under quotes, because that is not exactly we are going to interpret it now. So, this with minus E we will call it the charge density. Similarly, we have the spatial component here, which is minus I e phi star grad phi, so f and I minus phi I grad phi f star. This is phi I, phi f is essentially what we call the current density. So, the probability density and the probability current density we multiplied by the electric charge, we call it charge density and the current density respectively. I think this is with a minus sign already there, we will check that out. So, now with this I can write T f I as minus I integral j mu a mu d4 x, where j mu is rho j, the 4 vector current density. The charge density and the current density together considered as a 4 vector, which is the charge current 4 vector current density for this thing. So, what we have done is we had considered interacting picture in which the transition amplitude can be written in the first order perturbation in this fashion, and by considering the or interpreting them in terms of charge density and current density, we could write T f I as an interaction of the electromagnetic field represented by a mu with the 4 vector current density j mu. Okay. So, pictorially we can consider an electric current, say due to electron interacting with the electromagnetic field of something, whatever it is, represented by the electromagnetic potential a mu. So, this is your current j mu and this is a mu. So, the interaction is basically between the current and the electromagnetic potential, and the transition amplitude when you have an initial and final state wave functions included in the current or interaction amplitude, the transition amplitude is given by minus I j mu a mu over the volume d4 x. We will consider more aspects of this as we go. Now, let us look at this electromagnetic potential a mu a little more. So, we had first considered the free particle wave functions, the equation corresponding to that, the dynamical equation called the Klein-Gordon equation corresponding to that. Incidentally, the problem with the negative probability density is almost taken away. You remember in the last discussion we had said that rho is equal to twice E the normalization wave function when we consider the plane waves. Free particle can be considered as plane waves or superposition of plane waves, and then if there is any problem with any particular solution, then that is a difficulty that may linger in the more realistic solution, which is a superposition of all the plane wave solutions. So, plane wave solution had a problem that energy is going to be negative in some cases, which means that negative energy solutions exist, we have to do something about it. And then we saw that the probability density is equal to, or it is proportional to the energy, and therefore, when energy goes to negative values, then this probability density goes to negative values, and then therefore, we cannot interpret it physically as probability density. But here if we interpret it as charge density by multiplying the probability density, this whatever we had earlier called the probability density, by the electric charge of the particle concerned, we get charge density, and charge density, because electric charge can be either positive or negative, can be negative. So, no problems there. The problem still remains of the negative energy, and then we will come back to that later. And then we considered the interaction picture here, and the interaction picture we had introduced everything, and then we finally said that we could consider the transition amplitude in an interaction as product of the charge density, current density, and the electromagnetic potential, and integrate it over the volume. Before going into more details of these interactions, come back to the electromagnetic field in relativistic quantum mechanics. Let us consider the Maxwell's equation. In the non-relativistic form, classically we can write it as del dot E is equal to rho over epsilon 0. This rho is actually the charge density. We have the same, sometimes the same notation representing different things, but in depending on the context, I believe you will be able to, without confusion, understand what is what. So, curl of E is equal to minus dou B by dou T. The electrostatic potential is curl free, but electric potential due to change in magnetic field can be circular. Divergence of B is always 0. Curl of B is basically the current, but if you have changing electric field, then again you can have magnetic field, or the curl of magnetic field then is proportional to change in the rate of change of electric field. These are the Maxwell's equations. So, now what is E in this picture of potential? We have E equal to minus grad phi, which would have been the case when you have electrostatic potential, but the curl is not 0 here, it could be due to the change in the magnetic field. So, we can actually have a dou by dou t A mu, a non-gradient term. So, the curl of this need not to be 0, and B is equal to curl of the third component, the special component of the potential. Let me call these set of these equations Maxwell's equation, the well known Maxwell's equations 1, and electric field and magnetic field expressed in terms of A and phi as equation 2. Let us introduce an object f mu nu with two indices, conveniently written in a matrix form as minus E x minus E y minus E z as the first row plus E 1 0 minus B z B y as the second row, E 2 B z 0 minus B x as the third row, and E 3 minus B y B x 0. As it is clear from the explicit form, f mu nu is an antisymmetric matrix in this fashion, in this way of writing. It is actually an object which is antisymmetric under the exchange of mu and nu, first and second indices. Consider dou mu f mu nu. Let us take nu equal to, mu is summed over. So, nu is free, but take nu equal to 0 case, that will give you 0 f 0 0 minus 1 f 1 0 minus 2 f 2 0 minus 3 f 3 0 equal to first term is 0, I think is there. Second term dou mu is with a minus sign. So, it is minus dou by dou x, but there is already a minus sign there. This is a covariant vector. So, there is a minus sign associated with this. There is, it is plus here, therefore, f 1 0 1 0 is E x. Okay. So, I made a mistake here in the notation. It should have been written as E x, E y, E z, not E 1, E 2, E 3, because that is what the notation we are using. So, second one is E y dou by dou x of dou by of E y plus dou by dou z of E z, or this is essentially divergence of E, that is when nu equal to 0. So, we can say that dou mu f mu with nu equal to 0 is equal to rho by epsilon 0. If we consider the Lorentz-Heaviside units, epsilon 0 equal to 1 and mu 0 is equal to 1, therefore, similarly. This is why C is, we had taken C is equal to 1, H cross is equal to 1. So, in that unit it is equal to rho. Now, nu equal to 1 will give you, so this is 1, we already denoted two equations as 1 and 2. So, here this will be 3. So, when nu equal to 1, we have dou 0 f 0 1 minus dou 0 f dou 1 f 1 1 minus dou 2 f 2 1 minus dou 3 f 3 1. This is equal to dou 0 f 0 1. F 0 1 0 1 is minus E x. Dou 0 is dou by dou t minus E x. F 1 1 is 0, but then minus dou by dou 2 t is 1 over, sorry, dou by dou x with a minus sign, because it is a covariant derivative term. Then f 2 1, f 2 1 is b z with a positive sign, minus of minus. So, dou z f 3 1 is minus b y. Right. Now, this is equal to minus dou by dou t of E x plus dou by dou x of b z minus dou by dou z of b y. The term in the simple brackets is the x component of b curl of b. So, what we have here is curl of b x component of this minus time derivative of x component of E, and as per the Maxwell's equation, the last one, it is equal to x component of the current density J. And you can consider other components nu equal to 2 and nu equal to 3 to get the other parts of this equation, and finally, we will have curl of B minus dou E by dou T equal to J, or curl of B equal to J plus dou E by dou T, which is essentially given by considering dou mu f mu 1, f mu nu, f mu 2, f mu 3, etc. So, all of these things together, okay. So, will give you dou mu f mu nu, 0th component gave us rho, and the other components gave us j mu. So, this with j mu equal to rho and j is essentially a compact way of writing Maxwell's equations. Divergence of E equal to rho, which is essentially given by nu equal to 0, and the other 3 values of nu will give you curl of B equal to J plus dou E by dou T. So, these two equations, Maxwell's equations, can be represented in a compact way using f mu nu as dou mu f mu nu equal to j mu. We will see how the other two equations in the Maxwell's equation, set of Maxwell's equations, can be represented in a similar fashion. That we will do in the next discussion.